everyone. Let's wait for 5 minutes so that others can also join. Okay, so let's start. So, good afternoon, everyone. My name is Nidhi. I'll be taking your tutorials for this course on basic real analysis. So today we'll start with some problems related to infimum, supremum, and eventually we'll look at sequences, the convergence of sequences, how we define the convergence of sequence, and various other properties of sequences. So let us start. Firstly, let's look at what do we mean by a bounded set. So we'll just start with basic definitions. I'll recall things whatever they are required to do the problems. So, second. I guess there's some issue with my pencil. Just wait for 2 minutes. My screen is visible now. Can you please let me know if whatever I am writing it is visible to you? Can one of you just unmute yourself and let me know whether my screen is visible
Yes.
so that okay. Okay, so let's start with a bounded set. When do we call a set is bounded below? So, uh, bounded below. So, if suppose we have a subset of real number, suppose A is a subset of the set of real number. Yeah. If we have a subset of real number, we say that A is bounded below if there exists, if we can find some real number alpha. Alpha can be any real number, need not be an element of A, such that alpha is less than equal to A for every A in capital A. That means we have a collection of some real numbers in R. we call it A, and now we are saying that it is bounded below. By bounded below, we mean that there exists some real number, there exists we can find a real number such that it is lesser than or equal to each or every element of this set. Similarly, we have bounded above. Um, Similarly, we have the definition of bounded above set. And in this case, this alpha, we call this alpha as a lower bound. This alpha is called a lower bound of A. That means we can find a lower bound only if we know that a set is bounded below. So, uh, so technically speaking, mm, any real number alpha in R is called a lower bound of a bounded below set, bounded below set A, if alpha is less than equal to A for every A in R. So I hope this definition of bounded below and lower bound, this is clear. We'll be using these terms very frequently, so I wanted you all to be very familiar with these terms. When do we say a set is bounded below and what is a lower bound? Then next comes the notion of infimum. Similarly, you can visualize yourself what do we mean by bounded above set and what are the upper bounds of a set. Next comes the definition of infimum. So next is infimum of a bounded below set. So suppose A is a subset of R, the set of real numbers, is bounded below, and then we have a collection of lower bounds. Obviously, it is very clear that if alpha is a lower bound, suppose alpha is less than equal to A for every A in A, then clearly alpha minus 1 will also be less than equal to A for every A in A. That means if we can find one lower bound, we can eventually find a lot of other lower bounds as well. We collect those lower bounds, and I'll denote it as a set L. uh, Denote the set L to be collection of all lower bounds. Alpha is a lower bound of A. And then in this case, the infimum is actually the maximum value that is in alpha. So let's say infimum of A, this is equal to the greatest lower bound, the greatest element that we can find in this L, script L, greatest lower bound of A. Also, we have a definition in terms of epsilon. So let's look at that as well. So suppose A is a bounded below set. is bounded below. Then we have, we say alpha is infimum of A if for any epsilon positive. For any epsilon positive means epsilon can be any real number which is strictly positive, as small as we want. It can be 0.0001 as well, and 10 to the power 100 as well. Just a positive real number. So for any epsilon positive, there exists an x epsilon. There exists, that means we can find some x epsilon which is in A, such that this alpha plus epsilon is strictly greater than x epsilon. So basically, if suppose we have, this is alpha, if I take a slightly bigger value than alpha, suppose here it is alpha plus epsilon, then I should be able to find some element in the set A which is lesser than alpha plus epsilon. So basically it is somewhere here. So I hope this is clear how this definition is defined. This epsilon, x epsilon. We'll see while doing the problems that how this will be useful. So similarly, I want you to understand the concept of bounded above set, the upper bound, also the similar epsilon definition. So using this, let's start with some problem. In between the problem, while solving the problems, these things will become more clear. Question number 1. Let A and B be non-empty bounded. So by bounded, we mean bounded above as well as bounded below. Bounded subsets of R. Then prove that the infimum of the set A plus B is equal to infimum of A plus infimum of B. Now what do we mean by this A plus B? So A plus B is the collection of elements of the form A plus B, where this A comes from the set capital A and B comes from the set capital B. So this is how we define addition in of two sets. So let's see how we can prove this. So let's start with the notation. Let alpha be the infimum of the set A, beta be the infimum of B, and gamma be the infimum of A plus B. Now we need to show that. What do we need to show? That this gamma is equal to alpha plus beta. So any idea? So can you tell me how do we prove that two real numbers, basically these alpha, beta and gamma are real numbers? Alpha plus beta is a real number, gamma is a real number. How do we prove that two real numbers are equal? What is the basic idea? Or how do we prove that two sets are equal? This you must have done in your high school, no? If we have two sets, suppose S and T, there are two sets. We need to show that these two sets are equal. How do we prove? Any idea? Both contain same elements. So how, what's the standard way? Yeah, of course, when they both are equal, they both have same element. So basically we start with some element in S and show that this will be in T as well, which proves that S is a subset of T. And then we start with an element in T and show that it will be in S as well. This would imply that T is a subset of S. So basically, in order to prove that two sets are equal, we prove that both of them are contained in each other. Similarly, when it comes to proving that two real numbers are equal, we show that both are lesser than equal to each other. Basically, we show that gamma is less than equal to alpha plus beta and alpha plus beta is less than equal to gamma. This would eventually lead us to the fact that gamma will be equal to alpha plus beta. So this is the standard technique, how we prove any two real numbers are equal. It might seem very obvious, but yeah, we need to, when it comes to proving something, this is a standard way. So let's start with one side. Now, since alpha is infimum of A, that means it is the greatest lower bound. That means eventually it is lesser than equal to each element of the set. So this implies alpha is less than equal to A for every A in capital A. Similarly, since beta is infimum of B, that means beta is less than equal to B for every B in B. This implies alpha plus beta, this is less than equal to A plus B for every A in A, B in B. Now, if I take an arbitrary element in A plus B, let C belonging to A plus B be arbitrary. Now, this would imply that there exists some A in A, B in B such that C is equal to A plus B for some A in A and B in B. Now, by equation first, this implies alpha plus beta is less than equal to C. Or instead, I should write by first, we have alpha plus beta is less than equal to A plus B, which is equal to C. Now, what does this give? This implies, now this, since this C was an arbitrary element in A plus B, this tells us that alpha plus beta is less than equal to C for every C in A plus B. So what is alpha plus beta for A plus B? Can anyone tell me? I'm saying that alpha plus beta is lesser than equal to every element in A plus B. So what is alpha plus beta for A plus B? Yeah, it will be a lower bound, not infimum. We do not know whether it will be the greatest lower bound or not. But since we know that alpha plus beta is lesser than equal to every element in A plus B, therefore alpha plus beta is a lower bound for A plus B. This implies alpha plus beta, this is a real number, is a lower bound for A plus B. Now, what is the relation between lower bound and the infimum? This implies alpha plus beta and infimum A plus B. So what should come here? lesser than equal to, greater than equal to, equal to. We have alpha plus beta is a lower bound, and we know that infimum is the greatest lower bound. You can unmute yourself. No need to type every time. Just unmute yourself and let me know. So alpha plus beta will be alpha plus beta will be lesser than equal to infimum of a plus b, because infimum is the greatest lower bound and alpha plus beta is just a lower bound. And what was infimum of infimum of a plus b? Gamma. So therefore we get alpha plus beta is less than equal to gamma. This is our equation 2. So one inequality we got. Next we need to prove that gamma will be less than equal to alpha plus beta as well. Okay. For this, next we will be using that epsilon definition. So now let epsilon positive be arbitrary. Be arbitrary means it can be any positive real number. Then by above, let me write it as, this is a characterization of infimum. So I'll just mark this as star. By the statement star, we can find by star, there exists some a epsilon in A. Also for B also we can do the same thing, and B epsilon in B, such that now instead of epsilon I can take this to be epsilon by 2. You'll see why I took, or I'll tell you later. Epsilon. So we can find A epsilon and B epsilon in A and B respectively, such that the infimum over A plus A epsilon is, sorry, infimum plus epsilon. This epsilon is strictly greater than A epsilon. Similarly, we have for set B, infimum of B plus epsilon is strictly greater than B epsilon. Now, since this we had infimum of A is alpha plus epsilon is greater than A epsilon, and beta plus epsilon is strictly greater than B epsilon. Let's just add these two inequalities. So from here we'll get alpha plus beta plus 2 epsilon will be greater than A epsilon plus B epsilon. Now this A epsilon plus B epsilon was an element. This belongs to A plus B. So what is the relation between A epsilon plus B epsilon and infimum of A plus B? So please tell me what should come here, greater than or lesser than? Sorry? It is not a lower bound. It is an element. See, A epsilon plus B epsilon is an element of A plus B. The infimum is the greatest lower bound, so it will be greater than all the lower bounds. So each element will be greater than equal to the infimum. Okay. Now since A epsilon plus B epsilon is an element of A plus B, every element is always greater than or equal to its infimum. So this gives us alpha plus beta plus 2 epsilon is greater than strictly greater than gamma, because infimum of a plus b is gamma. Now this epsilon was arbitrary. I can take it as small as I want. So I will take it tending towards 0. So instead of so here, since we are getting 2 epsilon, just to make the things quite easier, I could start with epsilon by 2. That would give me nothing but, instead of epsilon, I'll be getting here, instead of 2 epsilon, I'll get epsilon. That's it. No big thing. Yeah. So now, since this epsilon positive was arbitrary, I can take it tending towards 0. Since epsilon positive is arbitrary, I take it tending towards 0, and we get alpha plus beta greater than equal to gamma. Now I'll mark it as equation 3, inequality 3. So by second and third, yeah, from second we get alpha plus beta less than equal to gamma. From third we get alpha plus beta greater than equal to gamma. This implies by second and third, alpha plus beta is equal to gamma. And hence, infimum of A plus infimum of B is equal to infimum of A plus B. I hope this is clear. Please let me know if you have any doubt anywhere throughout the proof. I would like you to go through it once again. So the main important thing is to understand the relation between the elements of a set, the lower bound of a set, the relation between lower bound and infimum and the elements of the set, and again this epsilon definition, this one. Similarly, I would like you to try yourself. In next class, we'll discuss that similar relation for supremum. I would like you to try it yourself first, and if you have any doubt, we can discuss it in the next class. So, prove that supremum of A plus B will be equal to supremum of A plus supremum of B. I would like you to go through the definitions of upper bound, supremum, and exactly in the similar way as we have proved the above uh, part for the infimum, it can be done. So I'll just leave it for you for the time being. Try yourself. We can discuss it in next class if you have any doubt. Then we have next question. Question number 2. Let R be a real number. Prove that there exists a sequence xn of rational numbers such that limit n tending to infinity xn is equal to r. So please tell me, are you all familiar with the term sequence? Okay. So can you just give me an idea what do we mean by sequence? When I say a sequence xn, what does it mean? An ordered collection of elements. So how many elements? Yeah, it is an ordered collection. One can also call it as a function from the set of natural numbers to the set of real numbers, which basically means we have something related to the first term, second term. So we have x1, x2, and so on up to infinity. So basically, we have a real number corresponding to each natural number. So corresponding to 1, we have x1. Corresponding to 2, we have x2 in R, and we write them in order. Okay. Next important thing here is the convergence. How do we say that limit n tending to infinity xn is R? Okay. So I'll start with the basic epsilon delta definition, and then try to make you understand how things are can be seen. So we say that limit n tending to infinity xn is, suppose, L, if for any given epsilon positive, there exists a natural number n such that mod xn minus L. Now mod xn minus L means the distance between xn and L. This is strictly less than epsilon for all n greater than equal to n. So we had a collection of elements. So we had x1, x2, and so on. We are saying that no matter how small epsilon is, if this is the point L in this real line, and this is L minus epsilon, L plus epsilon. I hope this is clear that this means minus epsilon less than xn minus L less than epsilon, which eventually means the terms xn are between L minus epsilon and L plus epsilon. So the statement says that there exists a stage n such that after that, so that means x capital N plus 1 and so on, after that all terms xn's are lying between L minus epsilon and L plus epsilon. So no matter how small epsilon you give, we can always find a stage such that after that all the terms in the sequence lie in this interval. So one can visualize this as bullet shot. Suppose this is a point and someone is just shot aiming at this point L, and after a stage all the bullets should be shot in between L minus epsilon and L plus epsilon. There can be finite number of shots outside as well, but after a stage the shot should be perfect enough that all the bullets are going near L. So if this happens, then we say that the sequence xn, that was the sequence of the bullet shots, yeah, this is converging to L. So in this case here, we need to show that if there is a real number, then I can always find a sequence of rational numbers, which is converging to this point R. So let's see how we can prove this. So I hope this epsilon definition is clear. How we are saying that a sequence is converging to some point L. If you have any doubt in this definition, please ask. Okay. Okay, then let's start with the proof. Now, suppose R is any real number. Then obviously we know that all real numbers are either rational or irrational. I'll start with the first case when I say that R is a rational number. The set Q denotes the set of rational numbers. So can you tell me in this case what sequence I can generate, what sequence I can construct which will converge to this point R? The sequence should be of rational numbers. I just need a collection of elements. Those elements can be same, different, anything, just an ordered collection which are eventually near R on the real line. This should be near R. Any idea? The constant sequence R itself. We can always construct a constant sequence. No? The sequence can be constant as well. If I take xn to be equal to R for every n in n. So what will be our sequence? If I just expand it, it will be R, R, R. So no matter how small epsilon we take, always xn minus R modulus will be R minus R, which is 0, which will be always less than epsilon because we are taking epsilon to be positive. So for any epsilon positive, mod xn minus R is always less than epsilon. That means xn is converging to R.
Ma'am, can you
Hmm.
again explain this?
The constant sequence, how it is converging to R.
Yes.
Okay. So when do we say that a sequence is convergent? So if suppose we are saying that limit n tending to infinity xn is L, that means for any epsilon positive, you give me an epsilon positive, I say that I can find a natural number n such that now this epsilon was in your hand, you gave me any epsilon positive, I'll give you back some n such that this mod xn minus L is less than epsilon for every n greater than equal to n. That means when we had the sequence x1, x2, x and so on, you give me some epsilon positive, I'll tell you that after this stage, all the terms will lie in the neighborhood of your epsilon. That's how we define the convergence. Now here I am saying we define the sequence xn to be equal to R for every n in n. That means our x1 is R, x2 is R, x3 is R and so on. Each element is equal to R. Now you give me any epsilon positive. Now for any epsilon positive, what will be mod xn minus R? This will be R minus R because each xn is just R. So this is 0. This will be always less than epsilon because you gave me a positive epsilon. Na? I'm saying that mod xn minus x, mod xn minus R is always 0, which will be less than any epsilon you give. And this is happening for every n greater than equal to 1. Now in this case, this capital N is 1. So this implies limit n tending to infinity xn is just R. Is it clear now? All we need to
Yes.
show all we need to show is that after some stage, all the points are in some neighborhood of the point R. So the problem was to find a sequence such that the elements are rational as well. In this case, since the given point was rational itself, so we didn't had to work anything. The main task of the question is to find a sequence such that each element is rational. In this case, since R is itself rational, I can take the constant sequence. Next comes the problematic case where this R is an irrational. Case 2, when R is irrational. Now we need to find a sequence. Suppose this is R. We need to find a sequence such that, again, after some stage, all the points lie in R minus epsilon to R plus epsilon. So for this, we'll have to use the density property of the set of real numbers. Are you all familiar with the density property? Okay, I'll just recall. So we have density property of R. I can just make note of all these basic things. That's very important. So it says that for any two real numbers, for any xy in R, such that either one of them is strictly lesser than the other one. That means basically these are two distinct real numbers. Then we can find a rational number such that x is strictly less than r strictly less than y. So basically, in layman language, we say that between any two real numbers, we can always find a rational number. They can be as small, because for example, we can have x to be 0.0001 and y to be 0.00001. Then also in between them, we can always find a rational number. This is the density property of R, and hence we say that the set of rationals is dense in set of real numbers. So next we'll be using this property to construct a sequence which is convergent to this R. Okay. Now since R minus 1 is strictly less than R plus 1, this implies by density, we can find a rational number. I'll call it as x1 in Q, the set of rational numbers, such that R minus 1 is strictly less than x1, strictly less than R plus 1. Similarly, since R minus 1 by 2 is strictly less than R plus 1 by 2, we can find there exists some x2 in Q such that R minus 1 by 2 is less than x2 less than R plus 1 by 2. And so on, we can construct a sequence. R minus 1 by n is strictly less than R plus 1 by n. This happens for every natural number. There exists xn in Q such that R minus 1 by n is strictly less than xn, strictly less than R plus 1 by n. Hence we got a sequence x1, x2, x3 and so on up till it will go up till infinity, such that r minus 1 by n is strictly less than xn, which is strictly less than r plus 1 by n. Now this implies this is happening for every n in n. Now this implies r minus 1 by n strictly less than xn minus r strictly less than 1 by n for every n in n. Now if a number is in between minus a and plus a, that means its modulus is strictly less than the positive term. Now this is happening for every n in n. Next we will be using the Archimedean property, again a big milestone of the real analysis course. These are basic things: the density property, Archimedean property, the definition of convergence. All these things are very basic and very important. So I'll just write the Archimedean property. Okay. Mm, Please check the spelling. This might made incorrect. Archimedean property. Let x be a real number. Then we can find a natural number. Instead I should write n in n such that not this will be strictly positive. If x is a strictly positive real number, then we can always find a natural number such that 1 by n is strictly less than x. A positive real number. Now using this, by Archimedean property, there exists some n naught in n such that, okay, so we should have started with epsilon, no? Okay. So till now we have constructed a sequence xn such that mod xn minus r is strictly less than n, strictly less than 1 by n. Now we will prove that the sequence xn is converging to 1 by n. So we claim that this sequence xn will converge. Instead I should write limit n tending to infinity xn is equal to r. So in order to prove that this sequence converges to r, we should start with an arbitrary epsilon. Now let epsilon positive be arbitrary. Now we need to show that there exists a stage such that after that mod xn minus r is strictly less than epsilon. Now since epsilon positive is arbitrary, epsilon is a positive real number, then by Archimedean property, we can find a natural number, I call it n naught, such that 1 by n naught is strictly less than epsilon. Now that means, this implies whenever small n is greater than equal to capital N naught, This implies 1 by n will be less than equal to 1 by n naught. Now that will give us, we know that xn minus r was strictly less than 1 by n. This is less than equal to 1 by n naught. This is less than equal to 1 by n naught whenever n is greater than equal to n naught. And now since we know that 1 by n naught is strictly less than epsilon by first and second. Therefore, we get mod xn minus r is strictly less than epsilon, and this is happening only when n is greater than equal to n naught. When small n is greater than equal to n naught, 1 by n is less than equal to 1 by n naught, and 1 by n naught is strictly less than epsilon by the Archimedean property. Therefore, now this gives us limit n tending to infinity xn is r. I hope this is clear how we use the density property and the Archimedean property in the case of irrationals. Please, you can ask if you have any doubt at any step which is not clear. So the aim of our aim was to find a sequence of rational numbers which is converging to R, which is an irrational number. Archimedean property. Archimedean property, it has various versions. The version that we are using here is this main one, this one, which says that if I have a positive real number, x is a positive real number, then I can always find a natural number. You can notice that this 1 by n, if n is a natural number, if we look at these numbers 1 by n, so 1 by 1 is 1, 1 by 2, 1 by 2, then we have 1 by 3, and so on. So, uh, no matter how small x is, suppose x was somewhere here, we can always find a natural number such that 1 by n will be lesser than equal to this number. So basically, yeah, if x was greater than 1, then obviously all 1 by n will be lesser than x. And if x was less than 1, then no matter how small I can take, because this, we all know that the sequence 1 by n is eventually going to 0. So we can find as small 1 by n as we want. Yeah, that is main thing that we used. Yeah, because we had arbitrary epsilon positive, we wanted something to be less than epsilon. Here we know that for small enough x, we can always find 1 by n less than x. Okay. Okay. Next we have the concept of subsequence. Let's see. Question number 3. Now suppose an is a sequence of real numbers such that its subsequences. So what do we mean by subsequence? Can anyone tell me? Subsequence an and a2n minus 1. You can just unmute yourself and let me know how much idea you have about subsequences so that I can start from there. Both. Has it been discussed in the theory classes? The topic of subsequence? If it's not, I'll explain. Just let me know. So when we have a set, we always have a subset. Subset is just a collection that has elements from this main set. Somewhat similarly, we have subsequences. Subsequence is a sequence itself. It has an ordering. It has infinite number of elements. But the main thing is that the terms are coming from the main sequence. For example, here we can see that A to N. It says that when we had the sequence AN, which had terms A1, A2, A3, and so on, out of these, we are taking just the terms A to N. 2N means all the even terms. So the subsequence was A2, A4, and so on. Similarly, the sequence A2N minus 1. So this it had we're taking n equals to 1, we get a1, n equals to 2, we get a3, and so on. So basically, this is a sequence itself and a subset of the main sequence as well. That's how we define the subsequences. So in this problem, it's saying that if we have a sequence an and it has two subsequences a2n and a2n minus 1, both are converging to same limits. Now a2n and a2n minus 1 are itself themselves sequence as well, so they can be convergent, divergent, converging to some limit n. Now they are saying this, the both the sequences are converging to same limit. Now we need to show that if that's the case, then the main sequence will also converge to the same limit. So let's see how to prove this.
Ma'am, there can be many subsequences possible for a sequence given.
Yeah.
So all subsequences limit would converge to the main to the limit of an.
Provided the sequence is convergent.
Uh, what, ma'am?
If the sequence is convergent, then all its subsequences will converge to same limit.
Okay, okay, okay.
In this case, we are given that the subsequences are convergent and they are converging to the same limit, but nothing is given about the main sequence. If the main sequence is convergent, then always all the subsequences will converge to the same limit. So is it clear?
Yes, ma'am.
Okay. Okay, now let's see how to prove this. So when the sequence is convergent, there is no issue. The problem occurs then when we do not know anything about this main sequence, but we have some idea about the subsequences. So now we are given that both the subsequences are converging to same limit. Now we suppose that we assume that both are converging to some L. Suppose limit n tending to infinity a to n is equal to L, and this is equal to limit n tending to infinity a to n minus 1 as well. Now by definition, this tells us, this implies for any epsilon positive, there exists a stage n1. I'm saying calling this n1 for corresponding to the first subsequence n1 and n, such that mod a to n minus L is less than epsilon for all n greater than equal to n1. Similarly, or instead of n, I should write it to be k because we have 2n. No? 2n greater than equal to n1. Yeah. And similarly for 2n minus 1, Similarly, for the same epsilon positive, epsilon I'm taking same, there exists n2 in n such that mod a2n minus 1 is less than minus l is less than epsilon for all 2n minus 1 greater than equal to n2. Now this says that n greater than equal to n1 by 2, and this says that n greater than equal to n2 plus 1 by 2. And what do we want? We want mod a n minus l to be less than epsilon for all n greater than equal to some n naught. Okay, so now let's see how does this a n minus l looks. Now this mod a n minus l is equal to, now this n can always be either even or odd. We have only two possibilities. So we have case 1 when n is odd. This implies this n can be written as 2m minus 1 for some m in n. Obviously, every odd number we can write it in this form. That means a n minus l is a 2m minus 1 minus l. Now this will be less than epsilon whenever 2m minus 1 is greater than equal to n2. That means we need this relation in terms of n. So just replacing m, wait a second. It should be n only. For all, we'll see how. Okay. Oh, okay, okay. पहले सही था. This was 2n greater than equal to n1 and 2n minus 1. From here we'll get for all m greater than equal to n2. Now this m is actually n plus 1 by 2. N plus 1 by 2 greater than equal to n2. That means mod a n minus l is less than epsilon for all n greater than equal to 2n2 minus 1. And then we have second case when n is even. In this case, n can be written as 2m for some m in n, and we get a n minus l. This is equal to a 2m minus l, and this is less than epsilon whenever m is greater than equal to n1. That means n by 2 is greater than equal to n1, which implies mod a n minus l, this is strictly less than epsilon for all n greater than equal to 2n1. Now let's mark this as equation 1 and this one as equation 2. From first and second, we can say that if n is greater than equal to maximum of 2n2 minus 1 and 2n1, in that case, mod an minus l is less than epsilon. See, the first equation says that mod an minus l is less than epsilon only if the subscript n is greater than 2n2 minus 1. And this one says that this happens only when n is greater than equal to 2n1. So if I take n to be greater than maximum of both the terms, both the cases can be included, and eventually we'll get mod an minus l less than epsilon. So therefore, by first and second, if we take this capital N to be maximum of 2n1 and 2n2 minus 1, we'll get mod an minus l less than epsilon for all n greater than equal to n, which gives us that limit n tending to infinity an is l. I hope this is clear. I got confused somewhere in the subsequences case. Yeah, I hope this is clear now. So basically, why is this happening? Because uh, the sequences a2n and a2n minus 1, they both eventually make the main sequence. So can anyone tell me what do we call the sets? Suppose A union B is giving us the universal set and A intersection B is empty. What are such sets called? When we have A union B to be the universal set and A intersection B is empty. Mutually exclusive. So can you see something similar over here? These two subsequences are also adding up eventually to give the main sequence, and both are completely distinct. And that is why, since both of them were converging to the same limit, eventually the whole sequence is converging to the same limit. That's the main idea. Okay, now let's move to next question.
Hello. Excuse me, ma'am.
Mhm. Yes.
Ma'am, I have little doubt. Like,
Hmm.
my concepts are not so strong. Like,
Hmm.
if I'm taking a sequence AN,
Hmm.
so in that we are considering the continuous numbers or just a numbers of elements, or it is a, real number line, or actually sequence. I'm not getting the better idea that what we are talking about here.
So you can
How?
start with the fact that sequence is just a function. We have a function whose domain is the set of natural numbers and codomain is the set of real numbers. So here we have 1, 2, 3, so on, and here we have the set of real numbers. Now this 1 is mapped to some real number, any real number. I'll call it as x1 because this is the image of 1. Then 2 is mapped to any real number. It can be same x1 also. It can be distinct, any point. So I call it as x2. Why x2? Because it is the image of element 2. Similarly, x3, this is x3. There need not be any relation between x1 and x2. Anyone can be bigger, anyone can be smaller. There is just some real numbers, x1, x2, x3, and so on. Now I collect these elements, x1, x2, x3, so on. We call this as a sequence. So the sequence has real numbers, but they are distinct. The elements are all real numbers, but they are distinct. They are corresponding to each natural number. So this set, if we see this as a set, this set has infinite elements. These elements can be repeated as well. So is this clear how this sequence is?
Yeah. Yes, ma'am. Actually, when sequence term is when we write the sequence, so just in my mind, it is going on that the sequence can be any number at random. Like it is not well defined. Ki it is in progression or not. So
It need
actually, I
not
was
be
getting
in progression.
it
Mhm.
can be progression. It can be at random any numbers. So I was getting confused with this. One more doubt is there. Like when we
Mhm.
are talking about somewhere, still I have a doubt in the continuity topics. Like
Mhm.
when we talk about epsilon and delta, so
Mhm.
that concept actually I'm thinking that epsilon is what? Because basically when we solve the theoretical question, main purpose is to we have to find the value of the epsilon where it
Mhm.
satisfies what the delta. That should be further. So that epsilon, it is very tough to find the particular epsilon. What I'm facing the problems while
Mhm.
going theoretically, not as a class intermediate level things, because there the continuity concepts are by differential method, but here the concept approach is something totally different. So
Mhm.
epsilon, what I think epsilon may be the very small gap between both, and we'll take the further any other mapping. So that mapping will be further means that mapping will also be less than that epsilon value. Then only that I think the limit will approach to that. No, something like this it is. I'm not getting that
So,
better idea. Also, can
so
you
you
explain
are you
it?
are asking about the definition of continuity or the
No, no,
definition
no,
of
no, no,
limit?
no, no. I'm
Limit.
not asking a definition. I have limits also. I have that we are in search of epsilon number. So
Hmm.
epsilon denotes which means it denotes the smallest number or something. Uh,
It can be anything. See, when we are talking about, for example, when we are talking about the definition of limit of a sequence. In that case, we say that for any epsilon positive, you give me any epsilon positive, I should be able to find a natural number n such that something happens for that, such that mod xn minus L is less than epsilon for all n greater than equal to capital N. Now this epsilon can be any positive real number. The fact that the main important thing is that for any corresponding to any epsilon positive, I should be able to find a stage. That stage will differ, obviously it will be depending on epsilon. We call this n to be a function of epsilon as well. This eventually comes in terms of epsilon. For example, when we proved above the sequence of irrationals, there was a relation between n and epsilon, that n was coming using the epsilon and the Archimedean property. So this epsilon can be any positive real number. Now when we are talking about small, so basically now this mod xn minus L less than epsilon, it depicts this interval around L. So we are saying that after a stage, all the elements of the sequence are lying in this interval. The elements can be anywhere, greater than L, lesser than L, anywhere, equal to L as well. But if I make this a shorter interval, that means my epsilon is smaller. Then also I should be able to find infinite number of elements over there. After a stage, at almost all elements. Then if I make epsilon more smaller, then also I should be able to get all the points. So this is how the notion of epsilon and n works. Epsilon can be anything. Corresponding to any epsilon, I should be able to find a stage n epsilon, such that after that something is happening. That's how
like
this
what
epsilon is.
I was actually what I was facing to get the value of epsilon it is very tough while solving the questions, because when we see the solution, so okay, according to them, so I'm understanding okay, this epsilon I take, so all the conditions are satisfying. But by
Mhm.
my own, I'm not able to predict that this will be
That
the
you
particular epsilon.
That you'll get after practicing a lot of problems.
Oh,
That's
that
not
only
an
I'm
easy
saying.
task. Yeah, yeah,
Yeah,
yeah.
yeah.
That will come with experience, with time. That will take time. These things are in the starting you will feel what maths has become. It was something else, and suddenly it's all English. So yeah, these things will take time. Don't worry. That's why I'm trying to
Thank you, ma'am.
prove
Thank you.
everything. Yeah, that's why I'm trying to
Yeah,
prove
no,
everything in detail.
yeah.
Okay.
Okay, ma'am. That's
Yeah.
why I want to go through the real analysis again because in books,
Uh-huh.
no, although I have done my MSc also, but my things are not clear. It is just the learning part and writing the exams. But actually, I want to understand the
Then
charm and
there's
beauty.
no sense of doing the things,
Uh,
na?
yeah, yeah, yeah. Thank you,
Just
ma'am.
for
Thank
the
you.
sake of exam.
Yeah,
Okay,
ma'am.
let's move to next problem. Now, if we have a sequence an, if an is bounded sequence and bn is another sequence that is converging to 0. Now, about an, we only know that the sequence is bounded and bn is a convergent sequence. Another sequence bn which converges to 0 show that the product sequence means the sequence whose each term is of the type an times bn is a product sequence also converges to 0. And what can we say about the product sequence if bn converges to some non-zero point? Now we are given two sequences an and bn. The sequence an is bounded. We do not know whether it is convergent or not. All we know is that it is bounded. By bounded, we means there exists some positive number m such that mod an is less than equal to m. This is all we know about the sequence an. And the sequence bn, it is convergent to 0. Now since, and this is happening for every n in n. Uh, and bn converges to 0. That means for any epsilon positive, there exists a stage n such that mod bn minus 0 is less than epsilon for all n greater than equal to capital N. So after capital N, all the terms are going near to 0. Next, they are asking us to prove that the sequence an bn. So let's define Cn to be an times Bn. So we have another sequence Cn. All of its terms are defined as an times Bn. We need to show that this sequence Cn is converging to 0. That means we need to see that the Cn minus 0, this is less than epsilon for after some stage. Now the Cn minus 0, this is just an Bn. But again, rest of the terms are 0. We know that this can be written as mod an mod bn. Now we'll use these two, equation first and second. Now since mod an is less than equal to m for every n, this is less than equal to m times mod bn and this is happening for every natural number n. Then I can write this to be equal to m mod bn minus 0. Now bn minus 0, we know that this is strictly less than epsilon. Bn minus 0 is strictly less than epsilon whenever n is capital less greater than equal to capital N. Now this is happening by first and this came by second. Now that means, sorry, this means mod Cn minus 0 was less than m times epsilon for all n greater than equal to n. Now, since this epsilon was arbitrary, I can replace this epsilon by m. You'll see why I took this. Epsilon is a positive number. Epsilon by m is also a positive number. I say that instead of epsilon, I will take epsilon by m. That's my wish. I wanted to do it this way. I'll take it this way. Now, this will give us epsilon by m over here and epsilon by m over here. Now, this gives us mod Cn minus 0. This is less than epsilon for all n greater than equal to capital N. Now, this stage is same as this stage. This gives us limit n tending to infinity. Cn is 0. Is it clear why I took epsilon by m instead of epsilon?
Yeah, ma'am. Got it.
And why this was important? So eventually we get that the sequence Cn is convergent. Now they are asking that what can we say if the sequence Bn is convergent but it is not converging to 0? Can you think of some example where Bn is An is a bounded sequence and Bn is a convergent sequence which is converging anywhere uh, not equal to 0, and in that case A and Bn is something else? Because obviously it should be something else, no? Otherwise, why would they ask such a question? Just look for some examples of sequences. Not necessarily to the greatest limit point. The thing is that in the case when Bn is converging to anywhere except 0, you can get anything. For example, the sequence A and Bn might not even be convergent. So we'll look at some example. I would like you to look for other examples as well. Now, if I take mm, take the sequence an to be minus 1 to the power n. So basically the terms will be just minus 1, 1, minus 1, 1, and so on. Oh, clearly this sequence is bounded. All the terms are lesser than equal to 1. Mod an is less than equal to 1 for every n in n. That means an is a bounded sequence. Now if I take bn to be the constant 1, we know that constant sequences are always convergent, as we had proved earlier also. The sequence bn is convergent and it is converging to 1. Now what will be the product sequence? Product sequence a and bn will be, again eventually this is same as an, 1 minus 1, 1 minus 1, and so on, which is, we all know that this is not convergent. Such sequences are called oscillating sequences because all the terms are eventually oscillating between 1 and minus 1, not convergent. Similarly, the next example could be, if we take, this is one set, then we have constant sequence 1. Obviously this is also bounded. Bn also constant sequence 1. In that case, a and bn is just 1, which is obviously again convergent. This is convergent. So basically, the main thing is that if bn is not converging to 0, then we cannot say anything about a and bn. But this is a very good result. We should always remember that if an is a bounded sequence and bn is converging to 0, then the product will always converge to 0. Nothing can be said about a and bn if the sequence bn is not converging to 0. You can yourself look for some other examples as well. So I hope this is clear. Let's move to next question number 5. Okay, so this will be a bigger. Let an be a sequence of real numbers. Any sequence, we do not know whether convergent or not. Now define Sn to be a1 plus a2, so on up till an upon n. Using the sequence an, now we are defining another sequence Sn. So if I write it in the form of summation, I can write it as summation I from 1 to n ai whole divided by n. Now we need to show that if the sequence an is monotone and bounded, then show that the sequence Sn is also monotone and bounded. Now what do we mean by monotone sequence? Yes?
Hello. Yeah,
Hmm?
it means ki either it is increasing or maybe decreasing. Only one trend will be there. Is it so?
Yes. And how do we write that a sequence is increasing or decreasing? Suppose we want to say
A,
that a sequence is
okay, I'll write
increasing.
for AI is greater than AJ for every I is greater than J. Otherwise, like something like that. You do.
Yeah. Yeah. We say a sequence an is, I'll be using this notation for increasing, if an plus 1 is greater than equal to an for every n in n. Each next term is greater than the previous one. Similarly, we have decreasing. Similarly, decreasing, if an plus 1 is less than equal to an for every n in n. Each next term is lesser than the previous one. So they are saying that if the sequence an, now we had a sequence an, we do not know anything about it. So if we are given that the sequence an is monotone and bounded, then it should be the sequence Sn, which was constructed using the elements of an, will also be monotone and bounded. Let's see how we can prove this. I'll prove it step by step. So without loss of generality, I'll start with the fact that an is increasing. Suppose, similarly, you can do things for decreasing sequences. Suppose an is an increasing sequence. And of course, it is bounded and bounded. This implies there exists some m positive such that mod an is less than equal to m for every n in n, and a n plus 1 is greater than equal to an for every n in n. Next, firstly, let's show that the sequence Sn is bounded as well. Now, for bounded, we need to show that mod Sn is less than equal to some fixed constant. So mod Sn, this is equal to, by definition, a1, a2, an upon n. Now we have triangles inequality for modulus. So yeah, since this n is positive number, I can take it outside the modulus into and so on up till an, which is less than equal to 1 by n mod a1 mod a2 mod an. This is by the triangles inequality for modulus. By triangles inequality of modulus function, which basically says that that is, we have mod a plus b is less than equal to mod a plus mod b for any real numbers a b. And obviously we can do this for n number of terms as well. Now since the sequence an was bounded, we know that an is less than equal to m for every n. So mod a1 is less than m, mod a2 is less than m, and up till mod an is also less than m. So this is less, I'll mark this as equation, this as 1, 2, this is less than equal to 1 by n, m, m, m. Now this was by first. Now since there are n times m, this is n m by n, which is just m. That means mod Sn is less than equal to m for every n in n. Therefore, the sequence Sn is bounded. We use the fact that an is bounded, and hence we concluded that the sequence Sn will also be bounded. And eventually, and they both will have same upper bound. Therefore, Sn is bounded as well. Next, we will show that the sequence Sn is increasing. That means we will show that Sn plus 1 minus Sn is greater than equal to 0. This
Uh,
will be our claim.
excuse me, ma'am. I
Yes.
can ask, what you have explained the triangle inequality. So what
Hmm.
I'm understanding, like geometrically, we can see that some of the two sides may be greater than equal to the third side,
Hmm.
maybe equal. But when we take into the end dimension, in the end sides, so what is the geometrical meaning? Can you explain that part? Like geometrically,
That
what
will
we can like for that?
that will that will be in n-dimensional world. So when we are talking about three terms, then we are in R3. So that will be eventually in Rn space. In Rn space, if you have gone through the normed linear space in your masters, you must have seen this type of triangles inequalities for the norm. So modulus is basically the norm with respect to the space R. Or you are asking just for mod
No,
A1
just I'm
plus
asking ki, whether still it will be with the n dimensional, still it will be the triangle only, but in dimension, n dimension.
So n dimension, you means this A and B
For,
to be replaced
uh,
by vectors?
yeah, ma'am. I'm just visualizing as a1 to an minus 1 will be one side, and another like whatever an will be the another side, like n dimension something. I'm not getting the clear picture of this. Geometrically, how I can visualize this relation that actually what it says.
Okay. So if we take A and B to be some vectors in Rn, because R in Rn the points see in R we have just real numbers. When we go to R2 or R3, we have vectors. So this A will be actually A1, A2 up till AN in Rn. So you're talking about A minus B, where A and B are vectors. I'm asking whether are you saying this?
No, I'm saying like mod of a plus b is
Hmm.
less than mod a plus mod b. By
Hmm.
induction, I can prove that it will satisfy for the n dimension also. By induction, I can do. But
Hmm.
geometrically, what is happening in this, I'm not getting the clear picture. Like geometrically, how it is possible?
This one. You want to
No,
see the
no,
geometric
no,
of this?
no. Like a mod of a1 plus a2 up to an will be less
Hmm.
than equal to mod a1 plus mod a2,
Ah, yeah,
so
this
on up
one,
to
right?
mod an. Yeah.
Hmm.
So geometrically, what does it represent then? This I'm not getting the clear picture that I'm saying.
Okay, I don't know either. This is just, I don't know. You can try search for it yourself and please let me know also.
Like I know that this proof can be done by induction, but
Yeah, yeah, it
like
can
if
be
I do,
proved by induction. So the main thing is this inequality
we have
only.
extended the
Using this
okay,
inequality, we are extending it.
um, okay,
Maybe
maybe it
it
is
doesn't have any geometric representation.
okay. Like I
Yeah.
thought ki, what the institution means ki, what the concept we develop for this part we can further extend by the induction. So to apply the higher applications, I
Yeah,
think
yeah,
something
yeah.
like that.
That's it. Yeah, that's it. No, nothing more than that. I don't think it has any geometrical interpretation. If it has, please let me know also. Yeah. Okay, so next we'll show that the sequence Sn will be increasing as well. So basically we'll show that Sn plus 1 minus Sn, this is positive. That will eventually give Sn plus 1 is greater than equal to Sn for every n and n. So let's look at the terms Sn plus 1 minus Sn. This is by definition. Here we will have up till an plus 1 on an plus 1 minus till an by n. Now if we take LCM and just add these two terms, we'll get n times a1 plus a2 and so on up till an plus 1 minus n plus 1 times a1 plus a2 and so on up till an on n plus 1. Now let's just look at the terms that are multiplied by a1. So here a1 is n times a1 and here we have minus n plus 1. Similarly, we have same things, a2 n minus n plus 1, and so on up till an we will have the same, and for an plus 1 we have just times n upon n into n plus 1. Now this will get cancelled out, so eventually we'll be left with n times an plus 1 minus a1 minus a2 minus so on up to an upon n times n plus 1. Now this n times an plus 1, I can write it as an plus 1 plus an plus 1 and so on up to n times. And I can just split it as an plus 1 minus a1 plus an plus 1 minus a2 and so on up to an plus 1 minus an. Now what can we say about the positive or negativeness of this term?
We are taking increasing function, no? We
an
are taking
sequence an is
increasing, no?
increasing. Yes.
Increasing, so it will be positive. Definitely, it will be positive.
Hmm. Since the sequence an is increasing, we always have a1 less than equal to a2 less than equal to a3 and so on up till an, therefore which is less than equal to an plus 1. So eventually an plus 1 minus an will be positive, an plus 1 minus a2 will be positive, all the terms will be positive. So this is, and obviously n times n plus 1 is also a positive term, so this will be greater than equal to 0. So we started with Sn plus 1 minus Sn, we got Sn plus 1 minus Sn is positive, therefore the sequence Sn is increasing. Now this happened because the sequence An was increasing. Therefore, if the sequence An is bounded and increasing, the sequence Sn will be bounded and increasing as well. Next, we will show that if the sequence is convergent, if it is converging to some A, then Sn will converge to A as well. Next, if the sequence An converges to some limb A, show that the sequence Sn converges to A as well. Okay. So again, we'll start with mod Sn minus A and try to show that this will be less than epsilon. Now mod Sn minus A, this will be by definition plus A2 up till An upon n minus A, which is mod A1 plus A2 An minus n upon n. Now again I'll split this na into up in the form a plus a plus a n times. So basically this will give us a1 minus a plus a2 minus a and so on up till an minus a upon n. Then we'll use the triangles inequality, which will give us mod a1 minus a upon n plus mod a2 minus a upon n and so on up to mod an minus a upon n. Now we will use the fact that an is convergent sequence and it is converging to A. Now since, let me mark this as equation 1. Since limit n tending to infinity an, this is A, this implies for any epsilon positive, there exists a stage n naught in n such that mod an minus a, this is less than epsilon for all n greater than equal to n naught. What happened? Oh, I guess there is some issue with my iPad. Okay, we have just 10 minutes left. I'll again start with the same problem in next class, and yeah, in YouTube, I'll write this again and provide you the notes. Don't worry about that. Anyways, the class was recorded, so you'll get that recording as well. Yeah, okay, then we'll start in next class and I'll repeat the same problem. Okay? If you have any doubt, you can ask. This is weekly class. On every Saturday, we'll have from, yeah, 3 to 5 p.m. Okay. I think there's some issue. Till I'm so sorry about my iPad. From next class, I'll keep it. No, no, it never happened before. Yeah, yeah, I'll provide you the recording, the notes, everything you'll be given. I'll upload this lecture session on YouTube. You can get the link.
Okay, thank you, ma'am. Very properly you have explained. I think now the concepts will be a little bit clear to me, and I'm sure that I'm going to enjoy this part. And now I'm able to see the things that why it is happening, because so far what the course we have done, actually just teacher also used to write on the board and we used to copy the things as it is without understanding. But here very each and every minute detail you have explained, and really I like that part. Now I feel a little bit confident that now I'll be able to understand this concept. I think further there will be we are going to go with the convergent test, I think.
Hmm.
uh,
Convergence of series.
Convergence of series, like what are different convergent tests. I think it is
Oh,
there in the that part. Then continuity and differentiability, all I think we are going to study in this course, I think so.
yeah, yeah, yeah. If you
Very
have any
properly.
specific topic that you want me to discuss, you can also tell me prior. Suppose, for example, if you want some topic to be discussed in next tutorial session,
we can
you tell
we
me
can
today
understand.
itself.
No, just now, actually, the total things like what we study up to class 12th, we enjoy, we understand also. But as we go into the undergraduate courses, you can understand that the without I've not taken any tuitions, any in my time there was no internet also, so you can
Mm-hmm.
understand that it is all things is abstract, and how difficult for a child to understand this abstract part. No, yeah, so
Yeah.
actually
Yeah,
I
suddenly,
got.
suddenly all calculations are turned into
But
philosophy.
are
Now
not
it's
there now.
philosophy.
Yeah, all things are abstract, just it is going
Yeah,
in the mind, and it is not with
yeah,
the numbers. So
yeah.
it is very difficult to understand the part unless the teacher explains. That's why it
Yeah.
is said, na, without teacher you can't get the knowledge, and by
Hmm.
interaction you can learn a lot. And this platform, na, I thanks NPTEL also that they have provided such a good platform, na, so that if the
Yeah.
child wants to study, na, he get the better concepts. Because what the courses I've done with the colleges, ma'am, it's just a degree they are giving. But here, na,
Mhm.
we get the thorough knowledge. We feel very confident, and we are enjoying also with this platform. Because, ma'am, to go in the good colleges, you have to give the entrance exam. And once the concept is not clear, you can't go in the good colleges. But here we
Hmm.
are getting the opportunity to talk with the experts and the teachers like you, like who have the thorough knowledge and good concept. So at least a drop also we are getting from you, na? That is actually a lot for me. It means a lot for us. No? Thank you, ma'am. Thank you for that.
Okay, okay. So I hope you all will be regular throughout this session, this
Yeah, ma'am. Of
semester.
course, of course, of course, of course.
Okay,
Thank you,
then
ma'am.
we'll meet next Saturday. I'll continue with the same problem, and then we'll look at some problems related to convergence of series and all.
Yes.
Okay, then.
Okay. Bye,
Hmm.
ma'am.